Welcome to the video lecture on graphing sine and cosine functions. In this lecture we're going to learn how to graph the basic sine and cosine curves as well as transformations of each. So let's start with the sine curve, sine of x. First of all, remember that sine has a period of 2 pi, which means that the sine of any angle plus a multiple of 2 pi will always give you back the same sine value. And we write that as sine of t plus 2n pi will give you back sine of t. Now to figure out the basic sine curve, we're going to need to know some points to plot, and I'm going to fill out this chart here based on our unit circle. So all of these values, remember, come from this unit circle that you want to have memorized, and the sine value is always the y coordinate of all these terminal points. Remember that for pi over 6 angles, the y coordinate is like a 1/2, either plus or minus. For pi over 4 angles, the y value is root 2 over 2, and for pi over 3 angles, the y coordinate is square root of 3 over 2. So using those values, let's fill out our chart. So for pi over 6, remember that the y value was 1/2 for that terminal point. So all these pi over 6's are going to be 1/2, but we will need to adjust the sign based on which quadrant we're in. All of these angles here are quadrant 1, and sine is positive in quadrant 1. All of these angles are quadrant 2, and sine is positive in quadrant 2. This is quadrant 3, so this sign should be negative, and this is quadrant 4, so this sign should be negative. Then for pi over 3 angles, remember pi over 3 was square root of 3 over 2, so this will be a root 3 over 2, root 3 over 2. This one down here will be a root 3 over 2, but it's negative because it's in quadrant 3, and this will be a negative root 3 over 2 as well. Pi over 4 angles were square root of 2 over 2. The quadrant 3 will be negative, and the quadrant 4 will be negative. And then what we're left with here in our chart are quadrant angles. So if sine of 0 is going to stay 0, sine of pi over 2, which is that 90 degrees, is 1. Sine of pi, which is 180 degrees, is 0. Sine of 3 pi over 2, which is 270 degrees, is negative 1. And sine of 2 pi gets you back to 0. So using those values, we are going to plot some points on our graph. So sine of 0 is 0. Let me plot all of my quadrant angles first, since they're nice values. Pi over 2 would be right here, and that had a sine value of 1. Sine of pi is 0. 3 pi over 2 would be right here, and that had a value of negative 1. And sine of 2 pi is 0. And then for these others, we're going to have to estimate. Pi over 6 would be right about here, so that's going to be a 1/2. Root 3 over 2 would be just a little bit bigger than that. 2 pi over 3 is root 3 over 2 as well. 3 pi over 4, 5 pi over 6 is about a 1/2 again. So you can kind of get the idea. We're going to have to estimate these points a little bit, but what you'll start to see is that these points form a nice curve. That is what we call our typical sine curve, and I can't draw very accurately with this pen that I'm using, but use your imagination. This is going to be the typical sine curve, and this is only one period length or one period cycle of the sine curve, but you want to have this shape memorized. Whenever you see that shape, you know you're talking about the sine curve. And it's got zeros at 0, pi, and 2 pi, a maximum at pi over 2 at a height of 1, and a minimum at 3 pi over 2 with a value of negative 1. Now because sine is periodic, that means that in the next length of 2 pi, so from 2 pi up to 4 pi, it's going to copy this exact same cycle because all of these y values will repeat again over here. So you're going to get that same sine shape from 2 pi to 4 pi, and we'd also get it over here from negative 2 pi up to 0. Okay, so there's your typical sine curve and showing its periodicity. Let's fill out a couple of the important characteristics of this graph. First of all, what's the domain of the sine curve? What x's do we get to use? I'm using every single x, so my domain is all reals, minus infinity up to infinity. What's the range? Well, how low and how high does this graph go? Because we're on that unit circle, which has a radius of 1, the smallest that this is going to get is -1, and the highest it's going to get is +1. And I hit those values, so use brackets. So -1 to 1. What kind of symmetry does this graph have? Well, if you think about how you could rotate this curve, if you were to rotate it around that origin 180 degrees, you would get that same graph back again. So it has symmetry around the origin. That also means that it's odd. And remember, the definition of sine being odd means sine of -x is equal to minus sine of x. Whenever a function is odd, you can sort of take that negative next to that x and pull it all the way out of your function and multiply by it. So that's our definition of being odd. What was the period of the sine curve? It was 2 pi because it completes one full cycle, goes through its max and its min in a length of 2 pi. Where does it have intercepts, x-intercepts? Where does it hit this x-axis? It hits it at 0, pi, 2 pi, 3 pi, 4 pi, -pi, and so on. So the way that we're going to generalize that is we're going to write k pi, where k is any integer. Remember, integers can be positive or negative. So if k is 0, 1, 2, 3, and so on, then we'll get all these positive intercepts. If k is -1, -2, -3, then we'll get all these negative intercepts. How about the extrema? Where does this graph have its maximums and its minimums? Well, it has maximums and minimums at pi over 2, 3 pi over 2. This one over here would be 5 pi over 2. And this one over here would be at 7 pi over 2. So it's all those odd multiples of pi over 2. So one way that we can generalize that would be to write that the extrema occur at 2k plus 1 times pi over 2, where again k is any integer. And why does that work? Well, if k is 0, then you just get 1 times pi over 2. If k is 1, 2 times 1, or 2 times 1 is 2, plus 1 is 3, so this would become a 3 pi over 2. If k is 2, you'll get 2 times 2 is 4, plus 1 is 5, so 5 pi over 2, and so on. So you keep generating all those odd numbers with this expression 2k plus 1. Okay, now that we know the basic graph of the sine curve, let's talk about what the different transformations that we've talked about in the past, how they apply to the sine curve. So this would be the most extensive way that you might see a sine function. It could have an a here out front. It could have a b being multiplied by your x, plus a c inside the parentheses, plus a d on the outside. Now remember, whenever we are trying to figure out our transformations, and there's a coefficient in front of x, you must always factor out the b first before you figure out what your transformations are. Otherwise, you're going to get that horizontal shift incorrect. So this is the same expression over here, but with that b factored out. So the a is out front still, the b is factored out, and that requires me to have an x plus c over b. If you were to redistribute this b across, you would see that you get back this original form. And then plus that d on the end. So what do all of these numbers do to our problem? Well, the a is out front of your function, which means it's going to affect the graph vertically. And if it's being multiplied, then that's going to either be a vertical stretch or a compression. And what that affects is how steep our graph goes through those maximums and minimums. And we call that amplitude. So this a is going to be the amplitude of our graph. It's going to tell us how high and how low we should go. Now the b that you factor out, that's next to the x, so that affects the graph horizontally as a stretch or compression. And remember that horizontally you kind of do the inverse, you do the opposite of what you would expect. So if b is a number bigger than 1, it's actually a compression, and if b is a fraction, then it's actually a stretch, and that's going to affect our period. And how does it affect our period? Well, there's going to be a little formula here that you're going to want to remember. The new period of our graph based on these transformations are going to be the old period, and the period of sine is normally 2 pi, divided by whatever this b is. So if b is bigger than 1, say b is 2, then that really means we're supposed to compress the graph by a half, which makes sense in this formula because we would then want to divide this period by 2 and cut it in half and compress it. So instead of having a period of 2 pi, now we would have a period of pi. So we'll use this quite often and you'll get practice using it. I should mention up here with amplitude, amplitude in general is this a value, but typically we think of the amplitude as always being positive. So sometimes you'll see it written as amplitude is the absolute value of a. So if there's a negative out front, then that would just flip your graph upside down, but your amplitude would just be the positive a value. Now going back up here, after we've factored out this b, this fraction right here that we're left with is being added or subtracted from that x. And whenever you're adding or subtracting next to that x, that's a horizontal shift backwards from what you would expect. So if this is plus, we're actually going to go minus or go left, and if this is minus, we're actually going to go right. This is called a phase shift when you're talking about trigonometric functions. So this would be just a phase shift, either left or right, by the value c over b, whatever that fraction is that you're left with after factoring out b. And as I mentioned, we'll get lots of practice doing this. Finally, the d on the end is being added off to the side, so that makes it a vertical shift, and if it's positive, you're going to shift up. If it's minus, you're going to shift down. So let's put into practice some of these transformations. Suppose that I have the function 2 sine x. Then we have only one thing new to our sine curve, and that's this 2 out front. And remember, when it's being multiplied out front, that's a vertical, in this case stretch, because 2 is greater than 1, and that just affects your amplitude. So all this implies is that we're going to graph our normal sine curve, but this time our amplitude is going to be 2 instead of 1. And all that means is that instead of having these max go up a height of 1, now it's going to need to go all the way up to 2. So this max, which is normally up here at 1, is being stretched vertically up to 2, and this min, which is normally at -1, is getting stretched down to -2. All the intercepts at 0, when you multiply those by 2, they still stay 0. So those aren't going to change. It's only the max and the min that will change. We don't have any new period. We don't have any phase shifts. So it's the same normal sine shape going up and then coming down, then going through your min and hitting 0 again. So there's our new sine curve with just a stretch, a vertical stretch by a factor of 2. So we just have this bigger amplitude. And if we continue this pattern, then this would go up and this would go down. And there's our new graph. Okay, let's take a look at the next example. This time we're trying to graph sine of 2x. So this time our 2 is next to the x, which makes this a horizontal, either stretch or compression. And since this number 2 is greater than 1, then it's going to be sort of the opposite or inverse of what we would expect. So this is going to be a horizontal compression by a factor of a half. Now what that affects, remember, is that period. So we are going to have a new period for this sine curve. Now the normal period is 2 pi, and the formula that you want to use is to take that 2 pi and divide it by whatever this b is, this number in front of x. And that means we're going to take 2 pi and we're going to divide it by 2, since that's what b is, and that makes the new period equal to pi. Now that's important, and it should make sense in the fact that we have a horizontal compression by a half. So instead of having your normal period from 0 all the way to 2 pi, we're compressing that horizontally. So now we're going to complete that whole cycle in half the width. So now we're only going to go from 0 up to pi and finish that normal cycle. So what you want to do when you're graphing this is think about where that sine curve is going to start. And in this case, we don't have any phase shifts at all. So we're just going to start at the origin like we normally do. But then we want to think about where we need to stop based on how wide our period is. And this time our period is pi. So I want to stop my cycle at pi. Halfway in between those, I also have another x-intercept. So this time I have another intercept at pi over 2. So now what I want to do is draw the normal sine cycle, the normal sine curve from 0 to pi. So we're going to sort of shrink it in a little bit here. I'm not changing the amplitude, I'm not doing any phase shifts, I'm not moving this up or down at all. So it's your normal sine curve, but it's just not going as wide as it normally would. So I would go up, and then down, and then hit back at 0 again. And these peaks and valleys are at 1 and -1 like normal. So there's the normal sine curve, but it's been condensed or compressed to fit between 0 and pi. And now all we have to do is finish repeating that pattern. So in the next width of pi, which would be from pi to 2 pi, I'm going to draw that same cycle again. And I'm just going to keep going to the right and to the left. So now I get twice as many sine curves in the width that I normally had before because I had that horizontal compression which shrunk the period down by a half. Okay, let's take a look at negative sine of x. What does this negative do out front to our graph? Well, that's a reflection, and when it's out front of your function, then it's a reflection over the x-axis. It's a reflection in the vertical direction. So all we're going to do is take our normal sine graph, which we see right here, and we're going to flip it upside down. So instead of going up, we're going to go down. Instead of going down, we're going to go up, and likewise continue the pattern. And there's our graph. Okay, the next one here is a little bit trickier because I have two different transformations. I have this 3 out front. The 3 causes a vertical stretch by a factor of 3. It's vertical because it's on the outside of that sine function. And remember that when you have this A out here, which is what we normally call it, that's your amplitude. So this is affecting the amplitude, and that means the new amplitude of my graph is going to be 3. So instead of only going 1 high, now we're going to go 3 high, just like that. Now before I can draw this graph, I also have to recognize that I have this minus pi over 4. There's no coefficient in front of that x, so I don't have to worry about any new period or anything like that. All I have to recognize is that this minus pi over 4 is inside of the parentheses next to that x, which makes it a horizontal shift. It's going to go opposite of what we would expect in terms of direction. And because it's a minus pi over 4, we're actually going to go right pi over 4. Whenever you have a horizontal shift left or right, this is called a phase shift. So we're going to go right pi over 4. Now my period, you want to always keep that in the back of your mind because that's very, very important whenever you're graphing trig functions, is what the period is supposed to be. Because there was no b in front of this x, my period is still 2 pi, and that's important to keep remembering, because when I go to graph this, I want to first figure out where my graph should start. And normally sine starts at the origin, but because of this phase shift, we want to shift that to the right pi over 4. So this mark right here is pi over 2, so pi over 4 would be right here. So this point at the origin is shifting right, so that means I have a new intercept at pi over 4. Similarly, this intercept at pi is going to shift over pi over 4 as well, and this intercept at 2 pi is going to shift over pi over 4 as well. Now because my graph here for this function has a period of 2 pi, that means I want to start at pi over 4 and I want to finish over a width of 2 pi. So my cycle length isn't changing, it's just shifting over. So we want to start here and we want to stop here, and we have this middle intercept in between. And I'm going to draw my normal sine curve. The only extra thing I'm going to add in is that new amplitude. So this time I want to make sure that this peak goes all the way up to 3, and this minimum goes all the way down to -3. And then you can repeat that pattern as you continue. Okay, so there would be my graph. Let's take a look at the next example. This time we have sine of x plus 2. Notice this time there are no parentheses around that 2. So that means or implies that it's off to the side, which implies that it's a vertical shift. And since it's plus 2, we are going to shift up 2. So we're going to take this normal sine curve. We're not changing the period. We're not changing the amplitude. We're not doing a phase shift. We're just taking this graph and we're raising it up 2 units. So you can take this intercept, which is normally at the origin, shift it up 2 units. This peak, which is normally at 1, is going to get shifted up 2 units to 3. Pi is going to shift up here to 2. This min at -1 shifts up to 1. And this 0 shifts up 2 to 2. So you draw your normal sine curve through those 5 points, and then you can just continue the graph from there. Continue the pattern. So same graph, just moved up 2 units. Alright, how about sine of -x minus 1? Now normally when we see this negative next to the x, we would say that that's a horizontal reflection. So this would be a reflection over the y-axis because it's next to that x. But I want to remind you that sine is an odd function, and what that means is sine of minus x is the same as pulling that negative out front and making it negative times sine of x. And that means this negative could be pulled out, and when the negative is out front, then that becomes a reflection over the x-axis. So these two reflections, in the case of the sine curve, actually would result in the same graph because it's an odd function. So flipping this thing upside down or flipping it over the y-axis should result in a similar looking graph. Now in addition to that reflection, we also have this -1. It's outside of the parentheses, so that's going to be a vertical shift down 1 unit. So we have to put the pieces together here. If you want to, you can do a sort of intermediate step and think about what this reflection would look like. When we just did it up above in an earlier example, you can either reflect it over the y or over the x. They mean exactly the same thing. Personally, I prefer to do things in the vertical direction as opposed to the horizontal direction, so I'm going to just think of this as flipping it upside down. So this would make your graph look like the same graph but flipped upside down. And now what we'd want to do is take this yellow graph that we have right here and shift everything down 1 unit. So right through the origin, now that's going to get shifted down 1. This point at -1 gets shifted down to -2. This goes down to -1. This height 1 gets shifted down to 0, and this gets shifted down to -1. So here's my 5 points, and through them I'm going to draw that upside down sine curve. And then you could continue the pattern from there. So if you need to do it in intermediate steps, that's fine too, or you can just jump directly to that red graph. Okay, the next one here, again, a little bit more complicated, and it's all because of this stuff next to that x. Whenever you have things acting on x, that's going to affect the graph in the horizontal direction, and that is always going to make the graph much tougher to deal with. Now, the most important thing that you need to do on this graph is recognize that I do have a 3 in front of that x. I have a coefficient in front of x. You have to factor out this 3 first before you correctly identify what your horizontal shifts and compressions and stretches are going to be. So let's go ahead and factor out this 3, and then in parentheses we're going to need to write down what would be left. I'm obviously going to have just the x left, but the tricky part is figuring out what needs to be right here in parentheses, so that if I were to redistribute back, I need to get back 3 pi over 2. So 3 times what gives me pi over 2? It's got to be a 3 times pi over 6. That way 3 cancels into the 6 twice, leaving me this pi over 2 back again. Now that's important because if I have factored out the 3, then I've got a minus pi over 6 left over here inside the parentheses. That is your horizontal shift, or what we call a phase shift. So we have a phase shift. Since it's negative, that means we're going to need to go right pi over 6. I also have this 3 in front of that x, that's that b number. Whenever you have a coefficient of x or a b, that means you're going to have a new period. This 3, since it's bigger than 1, is actually a horizontal compression by a third. And what that implies for us is that we are going to have a new period. It's the old period, which is normally 2 pi, and now we're dividing by whatever this b is. So my b is 3, so I'm going to have a new period of 2 pi over 3. In addition, I also have this minus and this 2. So the negative is going to result in a reflection over the x-axis, because that's in the vertical direction, it's out front of your sine curve, and then the 2 is going to give us a new amplitude of 2, and that's also known as a vertical stretch. So those are all of our different transformations. There's a lot of them to keep track of. So the first thing that I always consider when I'm doing this is that phase shift, because that's going to tell you where to start your sine curve. Normally the sine curve starts at the origin, and this time we need to shift that to the right pi over 6. So I am going to need to put in some extra little marks here. If this is pi, let me chop this interval up into 6 equal pieces. So I'm going to put in 2 here and 2 here. They're not quite equally spaced, so let me fix that just a little bit. This would be pi over 6. This would be 2 pi over 6, which is the same as pi over 3. This is pi over 2. This would be 4 pi over 6, which is 2 pi over 3, and this would be 5 pi over 6. You don't need to label them all, but you kind of need to know that you're chopping these up into 6 equal pieces. So I'm going to just add in a couple extra little tick marks everywhere. So if I'm shifting this to the right pi over 6, then instead of starting at the origin, now I want to start here. Now the next thing that I think about after I know where I want to start is I need to know where I should stop, and that's where the period comes in. I need my cycle to start at pi over 6 and go for a width of 2 pi over 3 and then stop. So what is 2 pi over 3 the same as? Let me rewrite that as a denominator of 6 since I'm dealing with 6 here. This is the same as 4 pi over 6. 2 pi over 3 and 4 pi over 6 mean the same thing. So if I go over 4 pi over 6's from where I'm starting, so here's 1 pi over 6 over 2, 3, 4. So this width from this first dot to this second dot has a width of 4 pi over 6. So that's where I want to start, and that's where I want to stop. Okay, that should be one complete cycle of my sine curve. So we're going to really shrink down this sine curve by a third. We're compressing it by a third. Now halfway in between, which would be right here, is going to be that other intercept that we always have in the middle. So you can put that dot in as well. And then finally, we've dealt with the phase shift, we've dealt with the compression. Now we need to deal with the amplitude and the reflection. So the amplitude was 2, so normally that would mean I would go up too high, but because we have a reflection, that means we're flipping this sine curve upside down, so now we're actually going to go down 2 first, and then we would go up 2. So here would be our sine curve. Go down and then go up, and we've done all of that in a compressed width, starting at pi over 6 and stopping at 5 pi over 6. So there would be my normal shape. Okay, so you can continue that pattern. Notice that I go over 2 of these marks here. So 2 over, 2 over, 2 over, 2 over, and so on. And you could continue this pattern. So if I go over 2, go over 2, over 2, and so on. So there's my new graph. Quite complicated, but start with that phase shift to know where to start. Find out what your period is so you know where to stop, and then based on your reflections and your amplitude, that'll tell you how high and how low to go. Okay, the next example here is asking us to find the absolute value of the sine of x graph. So let's figure out what that would do. Remember, what absolute values do is they make your graph, or they make your values positive. So anywhere where the sine graph is already positive, which means wherever it's above the x-axis, like all of these points here, that absolute value is not going to do anything to the graph. So this would stay exactly the same. But whenever we would get to points where normally the sine curve would be negative, when we take the absolute value of that, now it's going to become positive. So it's going to have that same shape, but it's just going to flip those over that x-axis. And then this is positive again, so it would stay the same. These are negative, so they would flip up, and it would look just like that. And you'll get little pointy intercepts here. So these are sharp turns in your graph. Okay? Now if we compare that to the graph of sine squared of x, that's not one we would be able to do by hand because it doesn't fit our normal transformations. So to do this, we're just going to use a calculator. Make sure that you are in radian mode whenever you're graphing, and I am up here. I'm going to go to my y equals buttoned, and I want sine of x squared. So when you type this in, you can't do the little square in the middle like we normally write it for shorthand. What you're going to want to write is parentheses sine of x, close the parentheses on the x, close the parentheses on the sine curve, and then hit your square on the outside. So you're going to want to type it in that way. And you can create any kind of window you want. I'm going to make my window match the dimensions of this grid that we see here. And on the left, it's starting at negative pi. So let's type in negative pi for x min. And you'll see that it instantly converts that to a decimal. This graph stops on the right over here at 3 pi. So let's type in 3 pi. And I have little tick marks at pi over 2's. So I'm going to let my x scale be pi divided by 2. And then my y min, it goes down to negative 3, and my y max goes up to 3, and now we can hit graph. Now it's sort of hard to see on this graph because we haven't zoomed in enough, but what I want you to notice is right here, it looks very similar to the last graph we did with that absolute value, but the big difference is that this is going to be curved at these intercepts instead of pointy. So it's going to have almost an identical shape as the original one that we had, but this time it's going to be curved almost like a little tiny U shape, and then it comes back around again. So not pointy so much as rounded. Okay, so very similar, but this one we have to do with our calculator unless you really wanted to make a table and plot lots of points. Okay, finally let's take a look at the graph of 1 over sine of x. Now you should all know by now that that's the reciprocal of sine of x, which we also know as cosecant of x. So the graph that we come up with here for our answer is going to be what the graph of cosecant should look like. Now because we're talking about a reciprocal graph, this graph that we're looking at here is sine of x, and we want 1 over it. So let's think about these zeros for a moment. If sine of x is 0 at 0, what's going to happen if we take 1 over that 0? Well, 1 over 0 blows up and goes to infinity or minus infinity. So that means at all of these intercepts, the graphs are going to blow up, and we call those asymptotes. So you are going to have asymptotes, vertical asymptotes, at every single one of these intercepts. So that means the graph of cosecant has x asymptotes, vertical asymptotes, at all these multiples of pi. Now let's take a look at what happens near those asymptotes. So take a look at this graph right here. These are all positive y values. And if we wanted to take 1 over those y values, what would happen to them? Well, they're getting smaller and smaller because they're getting closer and closer to 0. So what happens to 1 over something small? It gets big. In other words, it's going to go to infinity. Now, because these are all positive small values, then these are all going to go to positive infinite values. So that means this graph is going to go shooting up towards positive infinity. The same thing would happen over here as well, because these are all positive y values that are getting closer and closer to 0. So 1 over something really small gets really big, and they're all positive, so they're going to shoot up to positive infinity. Now when I get to these over here, these are negative values. So I'm still going to something small, because all of these, as I go this way along the graph, they're getting closer and closer to 0 and getting smaller and smaller, but they're all negative numbers. So 1 over something negative that's really small goes to something big but still negative, which means this is going to go towards minus infinity. So this time the graph on the other side of the asymptote is going to be shooting down. These are all negative y values as well, so this is going to be shooting down. These are all positive values that are getting close to 0, so I'm shooting up. These are all positives, so I'm going to be shooting up. These are all negatives, so I'm going to be shooting down. These are all negatives, so I'm going to be shooting down. So that's kind of how we figure out the behavior of the graph around the asymptotes, around those zeros. Now we just need to figure out how to fill in the graph in between. So look at this maximum. The largest value that sine takes on is 1. So what would be the reciprocal of 1? 1 over 1 stays 1. So this point right here is going to stay at a y value of 1. And 1 over the biggest value that the sine takes on becomes the smallest value that cosecant will take on. So this is going to go as low as 1, and then it's going to have to turn back around and shoot up towards that infinity. Over here, this hits negative 1. 1 over negative 1 stays negative 1. So this is going to reach up to that negative 1, but then it's going to have to turn back around again to shoot back down. So what we end up with are kind of these little U shapes. They go up, then down, and they're occurring through these, or in between each of these vertical asymptotes. And the cycle of cosecant needs 1 full up U, then followed by 1 full down U. So from here to here is 1 period of this cosecant graph. So the period of cosecant is 2 pi. From 0 to 2 pi, I get 1 full up U and 1 full down U. So just like the period of sine was 2 pi, so is the period of cosecant. So it's this basic shape right here that you want to have memorized. You've got vertical asymptotes at 0 pi and 2 pi, an up U shape, then a down U shape, and it's got a min at 1 and a max at negative 1. And then that pattern just repeats. Okay, so that's the graph of cosecant of x. Now we're going to talk about the graph of cosine of x. So to figure out the graph of cosine, we're going to need to remember that just like with sine, cosine repeats itself as we travel around that unit circle. So anytime we go through a multiple of 2 pi, you're still going to end up on that same terminal point on your unit circle. So cosine has a period of 2 pi as well. Let's fill out our little chart here. For the pi over 6 angles, and again, this is all coming from our unit circle, all the pi over 6 angles have an x value of square root of 3 over 2. The pi over 4s have an x of root 2 over 2, and the pi over 3s have a 1/2 for its x value. So that's what I'm going to use to fill out my chart. So pi over 6 is root 3 over 2. Cosine is positive in quadrant 1, negative in quadrant 2, negative in quadrant 3, positive in quadrant 4. The pi over 3s are 1/2 for x. So 1/2, it'll be negative in quadrant 2, negative in quadrant 3, positive in quadrant 4. The pi over 4s are root 2 over 2. It'll be negative in quadrant 2 and 3, positive in quadrant 4. And then for our quadrant angles, cosine of 0, the x value of 0 is actually 1, because we're on that x-axis at 1, 0. Cosine of 90 degrees is 0. Cosine of pi is negative 1. Cosine of 270, or 3 pi over 2, is back to 0. And cosine of 2 pi is back to 1. So that all comes from that unit circle. Now when we plot some of these points, I'm just going to plot those quadrant angles. 0, 1. So now I'm starting up here on the y-axis with a y-intercept of 1. At pi over 2, we're hitting 0. At pi, we're hitting negative 1. At 3 pi over 2, we're hitting 0 again. And at 2 pi, we're hitting 1. And then you can plot some of these additional points, but what we're going to end up seeing is this big sort of fancy U shape. Starts up, goes all the way down to -1, and then curves back up again. So this is the basic shape of the cosine graph, and then that just gets repeated as we progress through our period. Okay, so this is sort of the main graph right here that you want to have memorized. That's your basic cosine graph. So what makes it different from the sine curve is that it's starting up at a height of 1, then it only has 2 intercepts at pi over 2 and 3 pi over 2, and then it has this min at pi, and then it comes back up again at 2 pi. So let's fill in some of this important information. What would be the domain of this graph? Well, again, all x's got used, so my domain is all reals. What would be my range? My graph only goes as low as -1 and as high as 1. That's because of that unit circle. What kind of symmetry does this have? Well, if you take a look at this graph, you can reflect this whole graph over that y-axis and get the same graph on the other side. So this is symmetric with respect to the y-axis, which we also know as being an even function. And the definition of something being even means if you take cosine of -x, you should get back exactly the same thing as just cosine of positive x. So this negative inside of the parentheses just kind of disappears. It doesn't even need to be there. What's the period of cosine? Well, this starts its cycle at 0 and ends its cycle at 2 pi, so it's still 2 pi. Where does it have its intercepts? It hits at pi over 2 and 3 pi over 2, and if I kept going, this would be 5 pi over 2, 7 pi over 2, and so on. So it's all those odd multiples of pi over 2. So we write that as 2k plus 1 times pi over 2, where k is an integer. And that will generate all of those odd multiples of pi over 2. And then finally, where are the extrema? Well, we have maxes at 0 and 2 pi and a min at pi. So we've got extrema at 0, pi, 2 pi, 3 pi, 4 pi, and so on. So at all those multiples of pi. So k pi, where k is an integer. Now, just like we had with the sine curve, we can do all those same transformations with the cosine curve as well. So remember, this a out front affects your amplitude. The b that you pull out and factor out from your x affects your period. This leftover fraction, c over b, affects your phase shift. And your vertical translation is this d on the end. So let's try some out here. We want 2 times cosine x. So all we're doing is multiplying by a 2 out front of our function. That's a vertical stretch by a factor of 2. And all that affects, remember, is that amplitude. That's like that a that's out front. So this is going to have an amplitude of 2. So what that means is we're not changing the period, we're not doing a phase shift or anything like that. So we want that normal U shape, but this time I'm going to go as high as 2 and as low as -2. So I'm just stretching these maxes and mins up. The zeros won't change, they will stay 0. So I'm just going to draw that fancy U stretched up a little bit higher and lower than it was before. So then this would go through that same 0 and then come down a little lower, go through the same 0 but come down a little lower. Okay? Now what happens when we put that 2 next to the x? Then that becomes a horizontal compression because 2 is larger than 1. So this is a horizontal compression by a half, and that's important because that's going to give us a new period. So the formula still applies. It's 2 pi divided by whatever your b is, and in this problem my b is that 2. So I'm taking the normal period of 2 pi and I'm cutting it in half so it becomes just pi. So how do we draw this with this new horizontal compression? Well, we're not shifting anywhere, so this starting point will still be at 0, 1, but instead of stopping over here at 2 pi, now I need to stop at pi. And I'm going to stop up at a height of 1 like I'm supposed to over here, but now I'm just shortening up this width a little bit. And that means I have to hit my min right in the middle. So I'm actually now hitting my min at pi over 2, and we're going to draw that fancy U shape, but now it's starting at 0 and stopping at pi. So I've just sort of shrunken that little cycle width to half of its normal period length. So there's my new graph, and if we just repeat this cycle, I've got to start at pi and stop at 2 pi. So I'm going to draw that U shape, and so on. Okay? So we're just compressing that period by half. Alright, next example. Now we have a negative out front of our cosine, which is a reflection. Because it's out front, that's a vertical reflection over the x-axis. So all that does is flip this graph upside down. So instead of starting at 1, we're going to be down here at -1. This 0 will stay 0. Instead of being down here at -1, that flips up to 1. 0 stays 0. And this 1 flips down to -1. So it's that same U shape, but this time it's upside down. And then you could continue the pattern from there. Okay. Alright, now we're going to get a little more complicated because I see that horizontal shift happening right here. There's no b. The b here is just a 1, which is important. That means my period is not going to change. I do have a 3 out front, which is a vertical stretch by a factor of 3. And all that affects is my amplitude. So now my amplitude is going to be 3. But then this minus pi over 4 is a horizontal shift because it's still inside the parentheses. And since it's a minus, that means we're actually going to go right pi over 4. And remember, that's called a phase shift. So we have a phase shift right pi over 4. So I need to put in some marks here so I can show that pi over 4. Normally this would start up here at 0, 1. I'm going to have to shift that over pi over 4. So this is pi over 2. That makes this pi over 4. So I want to start right here now over pi over 4, but still at, oops, not at a height of 1. I forgot my amplitude. My amplitude is 3. So now I need to be all the way up here at 3. I'm stretching up that max to be up here. And then I'm shifting that over pi over 4. All right, how about some other marks? Let's put in our other pi over 4 marks as well. Now that I know where my graph should start, let's find out where it should stop. Normally it stops at 2 pi, and we're not changing the period, so it's still going to have a period of 2 pi, but this stopping point gets stretched up to a height of 3, and then we have to shift that over pi over 4. So I'm not going to stop at 2 pi, I'm going to stop at 2 pi plus pi over 4. So I'm going to stop over here at this little tick mark, but I'm stretching it up to that height of 3, that amplitude of 3. Halfway between these two marks, which normally would be at pi, that's the halfway mark, but we're shifting it over pi over 4. So this is now the new halfway mark. Instead of going to that minimum of -1, we're stretching that down to a minimum of -3. So I know where I start, I know where I stop, I know my middle point, and then we can put in our zeros as well. Normally I have a 0 at pi over 2, but that's going to get shifted to the right, pi over 4. Normally I have a 0 right here at this dot, and that's going to get shifted right, pi over 4. So I've got 1, 2, 3, 4, 5 dots that I know I need to go through, and we're just going to connect them with this U shape. And there's my cosine graph. And then you could continue the pattern from there. Okay? All right. Let's try the next one. Cosine of x plus 2. There's no parentheses this time, so the plus 2 is off to the side. That makes it a vertical shift up 2 units. So I'm just going to take my key points on my graph and shift them all up 2 units. So instead of being at 1 here, we're going to shift that up to 3. Instead of being at 0, this is going to shift up to 2. Oops. Instead of being at -1, that's going to shift up to 1. This 0 shifts up to 2, and this peak at 1 shifts up to 3. So here's my U shape. And then you can continue the pattern from there. Alright, cosine of -x minus a 1. So we know this -1 on the side, just like in the last example, is a vertical shift. And since it's minus, we're going to go down 1. But then what about this minus inside of the parentheses? Normally we would say that that's a reflection. And because it's next to that x, it would be a reflection over the y-axis in that horizontal direction. But think about the fact that cosine is an even function for a moment. What that means is cosine of minus x is exactly the same thing as cosine of positive x. So you could rewrite this function as just cosine of x minus a 1. That negative inside the parentheses doesn't need to be there, because when we reflect this over the y-axis, we get back exactly the same graph. So the reflection really doesn't do anything to the graph at all, because this is even. It already has that symmetry. So you can ignore doing the reflection, and the only thing that's going to have an impact on changing the graph is this vertical shift down 1. So all I have to do is take all these key points and move them down 1. So this peak moves down 1, this 0 moves down 1, this min moves down 1, this 0 moves down 1, and this peak moves down 1. So we get that U shape like this. And then you can continue the pattern from there. Okay? Alright, the next example here. -2 cosine parentheses pi over 6 minus x. Now you have to notice, by the way this is written, there is a coefficient in front of that x. It's really just this -1. So you do need to factor out that negative from the x, and I'm going to put the x first, just because that makes it more like our normal transformations where we have that bx plus c, and in this case we're going to need to figure out what should be left in parentheses so that if I were to redistribute my negative across, I should get back what I started with. Now this pi over 6 originally is positive, so I'm going to have a minus pi over 6 left over after I factor out the negative, so that when I redistribute I get back this quantity that I started with. Now think about this negative that's right in front of that x for a moment. This is like saying cosine of negative stuff. That's kind of a funny way to think about it. But remember, we said cosine is even. So if you have a negative next to this stuff, you can ignore it. It's not going to impact the graph at all because cosine is even, which means it's already a reflection over the y-axis. So this is the same as cosine of just that stuff without the minus there. So what that means for us is that I can ignore this negative and just think of this as cosine, negative 2 cosine parentheses x minus pi over 6. And now we've just cleaned it up a little bit, put it into a nicer form. We can disregard that reflection over that y-axis because the graph already has that reflection in place. So we don't need to worry about it, and that means we have fewer things to deal with. So what is going on here? Well, we've got a negative out front, so that's a reflection over the x-axis. The 2 is a vertical stretch, which gives us a new amplitude of 2. And then we also have this minus pi over 6, so that's going to be a phase shift, and because it's minus, we're going to go right pi over 6. Now, did I change my period at all? No. So we still want my cycle to have a width of pi, have a width of 2 pi, but we're shifting everything over pi over 6. So let's put in some marks here to show those pi over 6's. So I'm going to chop up from 0 to pi. I'm going to chop up this width right here into 6 equal pieces. So 1, 2, 3, 4, 5, and there's that 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Just makes it easier to account for those phase shifts. Alright, so normally the graph would start up here at 1, but we need to shift it to the right pi over 6. Then we have to take into account our amplitude, which is 2, so that would boost it up here, but then we also had a reflection which would actually flip it down to here. So did you catch all that? Here's what we did again. Normally we would start at 1, 0, 1. We're shifting that to the right, pi over 6. The amplitude would boost it up to 2, but the reflection is going to flip it over to negative 2. So that's where I want to start. Now where should I stop? Normally I stop up here at 2 pi, 1. So we're going to shift that right pi over 6. We're going to boost it up 2, and then we're going to reflect it. So now it's stopping down here at negative 2. Let's get the middle point as well. Normally my min is down here at negative 1. We're going to shift that right 1. We're going to boost it down to negative 2, but then the reflection is going to flip it up to positive 2. Now let's do our zeros. Normally this 0 would be right here. We're shifting it right pi over 2. 0 does not change from an amplitude because 2 times 0 will stay 0, and it doesn't get affected by the reflection either, because when you reflect 0, it stays at 0. So this will stay at that 0, but it's just been affected by the shift. My other 0 would be here, and I'm going to shift it right pi over 6, and the amplitude and the reflection won't change it. So now I have my 5 key points. It's that same cosine graph, but it's upside down. So it's going to be that U shape, but going upside down. So here's my graph, and then you could continue from here if you wanted to. Okay? Alright, the next graph here, I purposely left off the example graph because this one is going to be a little bit more tricky to deal with. First of all, you've got to notice that you have this coefficient in front of your x, so you want to factor that out first. So make this 1/2 cosine, pull out that 1/3, and then in parentheses you want to write what would be left. So I'm going to have that x left, I'm going to have a plus, and then 1/3 times what would give me pi over 2. So 1/3 times what would equal pi over 2. Well, if I wanted to solve this, if you could think of putting an x right here, I could just multiply both sides by 3. So that tells me that this x needs to be 3 pi over 2. So we'd have to have 3 pi over 2 right here. And the reason why that works, when I distribute, the 3's cancel out, giving me pi over 2 back again. Okay, so that's kind of how I figure it out. Now that I've factored everything out, this 1/2 is my new amplitude. So this time I'm not going as high as I normally am. I'm only going 1/2 high. This 1/3 is my b, which means I'm going to have a new period. Now be careful on this one. This is actually a fraction. So remember, these are normally horizontal stretches or compressions, and if your b is a fraction, then this is actually going to be a horizontal stretch by a factor of 3. So instead of having a normal period of 2 pi, we're going to stretch that out by a factor of 3. The formula still works because it's going to take 2 pi and it's always going to divide by whatever this b is. So when you divide by a fraction, that's the same as taking 2 pi, multiplying it by the reciprocal, which would become 3, and that is why we're stretching out this period from 2 pi, and now the new period is 6 pi. So we have an amplitude of 1/2, and we have this new, much wider period of 6 pi. And then I also have this 3 pi over 2 right here, which is my phase shift, because it's next to that x. It's positive, so we're actually going to need to go left 3 pi over 2. So I've got a new amplitude, a new period, and a new phase shift. That's a lot of things to keep track of. Now I'm going to make my own grid this time because this period is so large it wouldn't show up well on the other examples that I was using before. So first thing I always consider when I've got all this stuff going on is that phase shift, because that's always going to tell you where you should start. So this time I want to start to the left 3 pi over 2. Now remember, normally, let me just draw in what the normal U shape would look like. Instead of starting here, I need to move it left 3 pi over 2. So we need to put in some marks here. Here's negative pi over 2, negative 2 pi over 2, which would be negative pi, and negative 3 pi over 2. Now normally I would want to shift this point all the way over to here, but we have a new amplitude. So instead of going 1 high, we only want to go half high. So I only want to go half as much. So that's my starting point. I'm going to take this point away and move this stuff out of the way. Here's my starting point at a height of 1/2. Now, normally I would go a width of 2 pi, but this time we're going 6 pi for our period. So I need to figure out where 6 pi over would be. And 6 pi is going to be, let's count it out, from negative 3 pi over 2 to negative pi. That's just a width of pi over 2. And here's another width of pi over 2. So this is a whole width of pi right here. So here's 1 pi. I'm going to need to put in some more marks here. 1, 2, 3, 4, 5. Just put in a bunch, and now let's label them a little bit. Since these are going by pi over 2's, let's keep doing that. And I'll just do by pi's from this point on. 4 pi, 5 pi, 6 pi. Now I'm not going all the way to 6 pi because I didn't start at 0. I started over to the left. So I need to go 6 pi from this starting point. So here would be 1 whole pi, and then 2, 3, 4, 5, 6. So 6 pi stops me right here. Halfway in between would be 1, 2, 3 pi, and that's where I want that min to be, somewhere down here. Okay? So let's kind of fill in what we know here. We've got our starting point, we've got our stopping point, we've got our middle point, and I shouldn't draw that middle point as low as it is on that yellow curve. I want it to be half as high because we have that reduced amplitude. So let's call this -1/2 down here. And we would normally have some zeros in between these 2 points, so we're going to have to kind of estimate where that would be. This is 3 pi, so that's 1, 2, 3, 4, 5, 6 pi over 2's, so 1, 2, 3 pi over 2's would be halfway in between. That's where my 0 is going to be. 1, 2, 3 pi over 2's, that's where my 0 is going to be. So I should have an equal space between this dot, and equal space between this dot and this dot. So I've got 3 tick marks, 3 tick marks, 3 tick marks, 3 tick marks. I'm just trying to keep it all nice and balanced. Let me get some of these marks out of the way so we can draw our graph. So we now have 5 key points, and I'm just going to draw that U shape just like this. And there is my new graph, where the high points up here are going up 1/2, and this low point is going to -1/2. Started to the left 3 pi over 2, and I finished my cycle with a width of 6 pi. So that one's kind of confusing, but again, you want to start with that phase shift to know where you should start, and then you're going to count over to the right however much your period should be to know where you should stop. Halfway in between those 2 points should be your min, and then halfway between your min and your maxes should be those 2 zeros. And then you can label your amplitude or your scale on your graph to be whatever your amplitude should be. We'll practice that a little bit more on the next example. So this time we want to graph 3 cosine pi x. So this example is a little bit strange sometimes for students because we have this pi showing up, and sometimes that makes it look a little bit strange. So let's see what we've got going on. First of all, we have this 3, which means we're going to have a new amplitude equal to 3 due to that vertical stretch. And then this pi is being multiplied by x, so this pi is our b. That's going to be our horizontal stretch or compression, and because pi is bigger than 1, this is going to be actually a compression by a factor of pi. Now this is what's confusing for students. Whenever you have a horizontal stretch or compression, that means you have a new period. So use your formula. The formula is always 2 pi divided by b. And in this problem, our b is pi. So what happens, this is the strange part, the pi's cancel out, and we just get a period of 2. So there's no pi involved at all anymore. So here's what we're going to do for our graph. We're going to make our own graph this time because we have a slightly strange period going on. And we know that we want our cosine graph. And here's what you could do. One easy way to think about it is, here's what your normal cosine cycle looks like, correct? We don't have any phase shift left or right, so I don't have to worry about shifting it over at all. But I do want my amplitude to be 3, so we could make this start at 3 and go down to -3, so fit your scale to be what you want it to be for your amplitude, and then fix your scale on your x-axis to be whatever you want your period to be. We want this cycle to start at 0, and where do we want this cycle to stop? Since the period is 2 pi, then this has to stop at 2. Sorry, since the period is 2, not 2 pi, since the period is 2, I want it to stop at 2. And that means this min would have to be at 1. So this is a nice, easy way to figure out your graph. Draw what you know the sine curve is supposed to look like, or the cosine curve, what it's supposed to look like. Figure out what your period is, and that will affect how you label the scale on your x-axis. figure out what your amplitude should be, and that'll tell you how to make the scale on your y-axis. Let's try that again on this next example. So we want negative cosine pi over 4x minus pi over 2. Now, I see a coefficient in front of that x. So the very first thing I'm going to do is pull out pi over 4, and I'm going to have to figure out what needs to be left right here. Pi over 4 times what would give me back pi over 2? Well, to solve that, we could multiply by the reciprocal, 4 over pi. The pi's cancel out, and 2 goes into 4 twice, so this needs to be a 2 right here. And let's just double check that that seems right. Pi over 4 times 2, 2 goes into 4 twice, so I'm going to be able to cancel out a couple 2's, and I'll be left with this pi over 2. So that does work. So this negative is a reflection over the x-axis. This pi over 4 is a horizontal stretch or compression, and pi over 4 is actually kind of like 3/4, so that makes it a fraction. So this is actually going to be a horizontal stretch by pi over 4. And what that does is it gives us a new period. So let's figure out what the new period would be. It would be 2 pi divided by whatever this b is. So 2 pi divided by pi over 4. To clean that up, keep the 2 pi where it is, and then multiply by the reciprocal of 4 over pi. The pi's cancel out. 2 times 4 gives you 8. So now we're going to have a much bigger period of 8, and there's no pi again. The pi totally disappeared. Then finally, we also have this minus 2 in the parentheses, and that's a phase shift. And because it's minus, we're actually going to go right 2 units. So we've got a lot of things to put together. Let me draw my graph. Now, normally, the cosine graph is this U shape, just like that. But we have a phase shift this time. So this time I'm going to want to take this starting point, and I want to shift it over to the right 2 units. And then I want to draw my U shape. So there's my phase shift. Now how about my period? How should I draw this so that I get the right period? Well, we know that we want this to start to the right 2. And if I want my period to be 8, then where should this stop? It should stop 8 units over. So 2 plus 8 means this needs to stop at 10. And then one other thing that I have to add in that I haven't used yet is my reflection. I did my phase shift, I did my new period, I just haven't done my reflection. So all I need to do now is take this red graph and flip it over. Keep the units where they are. So this is still starting at 2 and stopping at 10, but now it's just starting below. And I didn't have an amplitude change, so this should be down at -1, and this should be up at +1. And if you wanted to continue the graph from there on, you certainly could. Okay, usually 1 cycle at the very least is good, and the directions in the problems would tell you. But I would probably say you're fine if you show me this 1 cycle, unless the problem specifically says to show more. Okay? Now, if you wanted to give a little bit more detail, where is this hitting right in the middle? Well, you know it needs to be evenly spaced, and from 2 to 10 is a distance of 8, so halfway in between would be a distance of 4. 2 plus 4 makes this 6. So you know that this is hitting 1 at 6. So again, show your phase shift first to know how far over to the right you need to be. Draw your cosine graph and use your period to tell you when that's supposed to stop at. So wherever your phase shift started at, plus whatever that period was supposed to be. So 2 plus 8 told me that I needed to stop at 10. Those are tricky, but if you practice, they will become easier. Alright, last one on this page is 1 over cosine x, and that's the reciprocal of cosine, which we know as the secant curve. So we are going to be graphing secant. Now it's kind of like how we did cosecant. Remember, 1 over something small, 1 over something that's going to 0, blows up and goes to infinity. And that means you're going to have a vertical asymptote. So wherever I have any zeros, 1 over that's going to go to infinity. So anywhere you have intercepts, those are going to become those vertical asymptotes. So for secant, we have vertical asymptotes at all those odd multiples of pi over 2. Then, to figure out the behavior near that asymptote, if you look at these y values, they're getting closer and closer to 0, so they're getting smaller and smaller, but they're all positive because they're above the x-axis. So that means 1 over something small gets big, and it's positive, so that means it should be blowing up towards positive infinity. So this is going to need to shoot up. Over here, these are all negative, so it's the same scenario, but this time we are going to 1 over something small that's negative, so that's going to go to something big that's negative, so we're going to go to minus infinity. So this time it's going to shoot down. These are negative, so I want to shoot down. These are positive, I want to shoot up. These are positive, I want to shoot up. These are negative, I want to shoot down. These are positive, I go up. These are negative, I go down. So that's kind of how you figure out all the directions around those asymptotes. And then finally, to fill in between, this peak is at 1, so that's the biggest that cosine takes on. 1 over 1 is going to stay 1, so this point is going to stay right there. So my graph has to go down, hit that point, and then turn back around and shoot back up again. This is negative 1, and 1 over negative 1 stays negative 1, so this is going to have to hit here, and then shoot back down again, hit here, shoot back up, hit here, and so on. So it looks very, very similar to that cosecant graph, but the only difference is that these intercepts cause us to have our asymptotes at slightly different values. So it's that same up and down U shape as the cosecant, but it's been shifted. So now we have our asymptotes at the pi over 2 multiples instead of the pi multiples. And just like with cosecant, the period here is one of these ups and one of these down U's. So you need both of them to make one full period. So the period of secant is 2 pi, just like it is for cosine. Okay, the last example we're going to do, we're actually going to do it in 2 different ways. And this is a pretty common type of problem you would see on tests and quizzes, and it's kind of tricky to do. So what we want to figure out is to try and come up with some kind of an equation that would represent this graph. And I'm going to need to put some little labels on these tick marks for us so that we can use them to help us out. We're going to assume that these are going by pi over 2's. I just didn't get labeled here on my graph, so I'm going to write those in. And what we want to do is come up with some kind of an equation for this graph. Now you have a couple possibilities because this has within it those U shapes that we're used to seeing with cosines, but it also has that up and down shape that you're used to seeing with sines as well. So we're going to do this in 2 different ways. The first way we're going to do it is using a sine curve, and then the second way we're going to do it is using a cosine curve. And it will generate the same graph, it'll just have a very different looking equation. Okay? So in order to do this using a sine curve, the very first thing you're going to need to do is to identify that typical sine curve shape. And you know from earlier today that that sine curve looks just like that, an up and a down. So we need to look for that. And I can't just start it right here because that's not going to be symmetric. We don't have the same up here as we have all this down here. So what you kind of need to notice is that halfway in between is sort of the symmetry line. So I need all of this up and all of this down to give me one full U shape. So here's my sine curve. My typical sine curve would be that shape right there. Now based on that blue curve right there, let's identify what transformations have taken place. So what's one thing that we could notice? Well, normally our sine curve is starting at 0, 0. This time our sine curve is starting down 1. So this is going to have a shift down 1 unit. Okay? What else can we notice? Look at its period. What do you notice about its period? Normally the period of sine is from 0 to 2 pi, so it completes this full cycle from 0 to 2 pi. Here I'm completing this cycle from 0 to pi. I stop the cycle at pi. So here my period is just pi. So what would that mean in terms of the kinds of compressions that I would need? We're compressing the period from 2 pi down to pi, which means we need a horizontal compression of a half. Remember that little b number? That's what b needs to be. B needs to be 2 so that the new period would be 2 pi divided by b to give me this pi period that I see in my graph. So I need a b of 2 in order to have the correct period. What else do I need? Let's talk about amplitude, another key piece of our sine curve. Normally the amplitude is 1. I go up 1 and I go down 1. Now look at my graph here. Remember, we are starting lower than we normally would, and we're not starting at the origin. So how high, what is this vertical height from here to here? That's called your amplitude. Well, I have to go up 2 units to go all the way up to that peak, and here I'd have to go down 2 units to go all the way to that min. And I'm basing that from that middle line, that imaginary symmetry line in the middle right here. So I go up 2 from there and down 2 from there. So my amplitude needs to be 2. And that is that A number that we always put out front of our sine curve. We're basically using this very general transformation that we talked about today. So we now know what our A should be. That's 2 for the amplitude. We know what this B should be because we wanted a period of 2. So this, we wanted a period of pi, so we needed a compression by a half. So B needs to be 2. We know that we wanted to go down 1, and that's what this D should be. So in order for the graph to go down 1, I would need D to be -1. The last thing we need to worry about is the phase shift. Is there a phase shift at all? Have I shifted my graph to the left or to the right? And in this case, no, it's still starting on that y-axis. I shifted it down, but I didn't shift it to the right or to the left at all. So there is no phase shift, so I don't have to worry about that. So now that we have all the pieces, we're just going to plug in A, we're going to plug in B, we're going to plug in our phase shift, and we're going to plug in our vertical shift. So the amplitude was 2, so I need my curve to have a coefficient of 2. We're using a sine curve. We wanted a compression of that period by a half, so we need that B to equal 2. There was no phase shift, so this is going to go to 0, so I don't need to add or subtract anything there. And my D was -1. So if you want to clean it up a little bit, this would be just 2 sine 2x minus 1. So there is one equation for this graph. Now we're going to do that all over again, but this time we're going to do it for cosine. So we're going to do y equals a cosine b of x plus c over b plus d. We're going to try to figure out what should our a be, what should our b be, what's our phase shift, and what's our vertical shift. So this time we need to think about that typical cosine shape, which is this U shape like this, from 0 to 2 pi. And I need to identify that U shape on this graph. So the U starts up high, so I'm going to have to start maybe here, and then I could do this whole U shape from here to here. And just like in the last one we did, there's sort of this imaginary horizontal line that's cutting that U shape in half. And normally that little dashed line would be where our x-axis is. But because we have a shift, this is being shifted down. So what is my shift? We're going down 1 unit, just like we did for the sine curve. That hasn't changed. So this whole graph, instead of being centered through that x-axis, now it's being centered through a horizontal line that's down 1. So that means I want to go down 1 and have a d, this vertical shift, equal to -1. So that hasn't changed. That's the same as my sine curve example. All right, what's the next thing that we looked at? We looked at period. So has the period changed? Is the period going to be any different? Well, remember, this is pi over 2, this is pi, this is 3 pi over 2, this is 2 pi. So we are starting here, which looks to be at about pi over 4, and we're stopping here. So we're going from here to here. Let me use a different color. In how much of a width? So this is pi over 4. So this much is pi over 4. Another pi over 4 makes pi over 2. Another pi over 4 and another pi over 4. That's 4 pi over 4s. So I complete this whole blue cycle in 4 widths of pi over 4s. 4 pi over 4s is just pi. So I'm completing this whole cycle in a width of pi. So my period is pi, just like it was for the sine curve. And that's going to be typical. Your period should be the same whether you use cosine or whether you use sine. And because the period is normally supposed to be 2 pi, that means we have to compress it by a half, which implies that this b number is going to need to be a 2, because that will give us a horizontal compression by 1 over 2. Alright, so far the shift down and the period remains the same as how we did it with our sine curve. One thing that is different is we have a phase shift that we didn't have with our sine curve. If you look at this, that u started up here over to the right pi over 4. So we have a phase shift right pi over 4. This u didn't start on the y-axis. It started shifted over. So if we want to go right pi over 4, then that means right up here inside our parentheses, we need to be seeing a minus pi over 4 in those parentheses, where that c over b is. If you want it to go to the right, you have to use a minus in front, because remember, opposite signs. Alright, how about the amplitude? Has that changed at all? No. Here's that imaginary line that's cutting this U shape in half, and I have to go up 2 units to reach that peak from that imaginary line, and I have to go down 2 units from that imaginary line to hit my min. So my amplitude is half of that full length from the max to the min. Divide that by 2, that's your amplitude. So my amplitude is still a 2 in this problem, which means that's going to be our A. So let's just put it all together. My equation will be y equals, the amplitude's 2. I'm using a cosine. My b is 2 because we had a period change. We cut it in half by 2. I did have a phase shift, so I need an x minus pi over 4. And then we had that vertical shift down 1. So putting it all together gives me that. Now there is certainly more than one answer for all of these. If you had chosen the U shape way over here instead of the one that I chose, then you would have a totally different phase shift. That's okay, because cosine is periodic. There's always going to be an infinite number of possibilities. And the same would be true for the sine curve. If you had chosen a different sine wave right here, for example, that would have given you a different equation than what I chose. So there's always more than one solution to these types of problems. I always tend to look for the easiest sine curve or cosine curve that's closest to the origin, so that I minimize that phase shift as much as possible. Alright, this is pretty tough stuff, graphing sine and cosine functions, and it takes lots of practice. So keep working at it and you'll get it. Good luck. That concludes our lecture on graphing sine and cosine functions.